Today in this video we will see relationship between modulus of elasticity and modulus of rigidity. See this cube ABCD subjected to tangential shear force tau. See this tau, this tau, this tau and this CB tau. Due to this tangential shear force, there is distortion in this cube. See this D dash, original side see CD, and due to shear force C dash D dash distortion, there is D and D dash change in length to this cube. See this cube diagonal BD, and after acting tangential shear force, this diagonal changes BD dash. This diagonal increases, elongation occurs in this BD, and after tangential force, this BD goes to BD dash. Okay, and similarly, due to this tangential shear force, there is compression occur in this AC dash diagonal. Real diagonal is AC, but due to this tangential shear force, there is decrease in length in this AC diagonal, and this decrease in length is AC dash. Okay, now we will see relationship between modulus of elasticity and modulus of rigidity in this derivation. See this original block seen like this after distortion. This is B and this is A. We will see step by step this derivation. Now first let's see strain in diagonal BD. Strain is change in length to the original length. So strain in this diagonal BD is change in length to the original length. Change in length is BD1 minus BD. See this BD1, that means this BD dash, BD dash minus BD. Right here first strain in diagonal BD. Strain E and diagonal BD is equal to change in length is BD dash minus BD upon original length is BD. Original length of that cube diagonal is BD, and change in length is this BD dash minus BD. That means this much length is change in length. See D dash and M is change in length. Consider this BD equal to BM, and due to this tangential shear force, there is change in length D dash M, and this change in length D dash M is nothing but the BD dash minus BD. Okay. Draw perpendicular line which meets at M on BD1. See this BD1, draw perpendicular line from D, and at point M draw line which meets at M on BD1. See this perpendicular line. Since due to small distortion from D to D dash, see this small distortion from D to D dash, the angle DBD1 is, this angle DBD1 is very small. Why this angle very small? Due to tangential force acting on this cube, there is distortion in the in this cube, and distortion is very small, and due to this very small distortion there is angle is also very small. DD dash, angle DB and D dash is very small. Alright, next slide. Draw a perpendicular line which meets at C, this perpendicular line which meets at M on BD1. Since due to small distortion from D to D dash, the angle DBD1 is very small. DBD1, that means we notify it D dash, DBD dash, upper side dash, DBD dash is very small. Therefore, dB is equal to dm. This dB is equal to dm. This BD is equal to BM. I already explained it. See here, I already explained it. BD is equal to BM. Now see, this EBD is equal to BD dash minus BD upon BD. Put this BD is equal to BM, that means BD dash is BD dash minus BM upon BD. Right, for this EBD is equal to B dash minus BD, BD dash minus BD upon minus BD upon BD. For this BD, put BM, BD dash minus BM upon BD. This is strain in diagonal. And BD dash minus BD dash minus BM. Now, this BD dash minus BM, see, this BD dash minus BD dash minus BM is nothing but the D dash M. Put this equation number 1. Next, consider this triangle D dash MD. Angle D dash MD is equal to 90 degree. Angle MD dash D is equal to 45 degree. Angle D dash D is equal to 45 degree. Consider cos 45 degree. Cos theta is equal to adjacent side upon hypotenuse. See, this theta is 45 degree and cos 45 degree is equal to this adjacent side upon this hypotenuse. Adjacent side is D dash M and hypotenuse is D dash D. Therefore, this D dash M is equal to D dash D multiplied by cos 45 degree. Next, consider ABD. This ABD, right angle triangle. ABD. By applying Pythagoras theorem, this BD hypotenuse is equal to square root of AB square plus AD square. And in this cube, see, in this cube, all four sides are equal. AB is equal to AD. Right? BD is equal to AD square plus AD square. Square root of 2 AD square. BD is root 2 AD. This BD is root 2 AD. This is equation number B, and this is equation number A. Put this equation A and equation B in equation 1. Equation 1 is strain in BD is equal to this equation 1. EBD is equal to d dash m upon BD. And from equation A, d dash m is d dash d into cos 45 degree. Upon BD is root 2 AD. Cos 45 is 1 upon root 2. Sorry. Into 1 upon root 2, and cos 45 is 1 upon root 2. Therefore, EBD is d dash d upon AD into 1 by 2. Now next, consider A, D and D dash, AD D dash triangle. Consider this AD D dash triangle. Consider triangle ADD dash, and this angle is phi, strain phi, due to, first see, consider triangle D dash DA, you may call it D dash DA. Due to this tangential shear force, there is distortion in this CD side, and distortion is DD dash. Distortion is very small. See, tan phi is equal to opposite side upon adjacent side, D dash D upon AD. And this, due to this distortion is very small, there is angle is also very small, and when for tan angle is very small, tan 0 is equal to 0, and angle is very small, tan phi is equal to phi. Therefore phi is equal to d dash d upon AD. Put this equation 3 in this equation B. D dash d upon AD, d dash d upon AD is nothing but the phi. Therefore EBD is equal to strain in diagonal is equal to phi into 1 by 2. That means 1 by 2 into phi. This is the strain in this cubic diameter. Okay. Now we know that modulus of rigidity is shear stress to the shear strain. Next see, we know that modulus of rigidity denoted by G is shear stress denoted by tau and shear strain denoted by phi. Therefore this shear strain is equal to shear stress to the modulus of rigidity G. Put this phi in EBD for and C. Put this shear strain in diagonal. Therefore EBD is equal to tau by G into 1 by 2. That means tau by 2G. This is equation D. See here, due to this tangential shear stress, there is increase in diagonal BD. That means longitudinal strain seen in diagonal BD, and also this lateral strain due to this tangential shear force, there is lateral strain also seen in diagonal AC, and this lateral strain is compressive lateral strain. There is decrease in this AC diagonal. See this, due to this shear force there is increase in this diagonal, longitudinal strain increases, and lateral strain, this AC lateral strain decreases. right here, due to shear stress, the diagonal BD is subjected to a tensile stress. Due to this, due to this shear stress, there is in diagonal BD tensile tensile stress seen, and in diagonal AC compressive stress is seen. Now tensile strain in BD due to tensile stress. In this BD, tensile strain in BD due to tensile stress in BD. See, with the help of Young's modulus formula, stress is Young's modulus is stress upon strain, stress here shear stress upon strain, and E is equal to shear stress upon Young's modulus. With the help of this, tensile strain in BD due to tensile stress in BD is tau by E. Here stress is not sigma. Here stress is tau, shear stress. That's why tau by E, strain, tensile strain. Now tensile strain in BD due to compressive stress in AC. There is also due to this compressive stress in AC, there is also strain seen in this diagonal BD. When this tangential shear force acting on this cube, there is tensile stress seen in BD due to this tangential shear force, and when this tangential shear force act, there is compressive shear force acting in AC, and due to this compressive shear force acting in AC, there is also stress seen in BD. That's why, right, tensile strain in BD due to compressive stress in AC. and this strain is lateral strain. Tensile strain in BD due to compressive stress in AC is lateral strain. See, with the help of this Poisson's ratio formula, Poisson's ratio is lateral strain to the longitudinal strain, and lateral strain is mu into E. Therefore, this Poisson's ratio mu into longitudinal strain is tau by E here. If you see previous lectures, then you grasp this topic very clearly and early. Total strain in diagonal BD. EBD is equal to this plus this total strain in diagonal BD tau by E plus E plus mu into tau by E. Take common this tau by E and 1 plus mu. Equation E. Next, compare this equation E and this equation D. EBD is equal to EBD. Tau by 2G is equal to tau by E 1 plus mu. Tau get cancelled. E is equal to 2G 1 plus mu, and this is the relation between Young's modulus and shear modulus. Young's modulus is nothing but the stress upon strain. Shear modulus is nothing but the shear stress upon shear strain, and shear modulus is denoted by capital G, and Poisson's ratio is nothing but the lateral strain to the longitudinal strain. E is equal to 2G in bracket 1 plus mu. This is relationship between Young's modulus and shear modulus. Thank you very much.